So here is what we have been talking about. And we talked about the coordinate frames. The first and foremost coordinate frame that we talk about is the inertial coordinate frame. That coordinate frame is earth centered, earth fixed, and we are using northeast down. So basically thumb is X, first finger is Y, and middle finger is Z. So it is supposed to be northeast down. So thumb is pointing towards north, first finger pointing towards east, and the middle finger is pointing towards down. This is the aircraft convention. In the textbooks of flight mechanics, as a matter of fact, whatever, even if you use an autopilot like Pickhawk or OpenMP or any other micropilot software, they use this northeast down configuration to describe the fixed wing aircraft dynamics. So why do we need all these different frames? Because please understand, aircraft is going to perform a very complex maneuver. There will be forces acting on that aircraft that will be dependent on maybe the airspeed, aerodynamic forces, aircraft control forces. So all these forces, they act in their individual frames. So in order to analyze this complicated multi-body dynamics, we need to understand where the forces are, where the moments are, what velocities are interacting on the aircraft, and how they are influencing the dynamics of the aircraft. So that's why we have these different frames. But at any rate, the first frame is going to be the inertial frame. Inertial means it's a fixed frame. That is earth center, earth fixed, which means we assume the earth to be flat, and that northeast down frame is located at the center of the earth, and it is fixed. Earth is not rotating, the frame is not rotating. So that is extremely important. Then please understand, there are different ways to describe the orientation of the aircraft. The alternate word for orientation is called attitude. So attitude of the aircraft means the orientation of the aircraft. Attitude is orientation, altitude is height. Attitude and altitude. So if you look at the attitude of the aircraft, there are basically three angles that describe the rotation of the aircraft. First is heading, which means in what orientation the aircraft is going forward. That heading is also called as yaw, which means rotation about z-axis. Rotation about z-axis. Next thing is elevation, which is theta, which is how elevated the aircraft is, which is the rotation about y. And so that is pitch. And bank or roll is the rotation about x. So for an example, this is the aircraft yaw, this is aircraft pitch, and this is aircraft roll. So these are the three angles that describe the attitude of the aircraft or the orientation of the aircraft. Here is the classic problem with these angles. And if you have done the aircraft simulation, I will actually show you what happens. The Euler angles have mathematical singularity, which means at 90-degree pitch, roll and yaw become one. At 90-degree pitch, roll and yaw become one. And I will show you how actually that happens in an actual animation. So the alternate approach is using something called as quaternions. Quaternions are hyperplanes, which means, so if we live in a three-dimensional world, if we have x, y, and z axis, if we add one more axis, it goes hyper. So basically, quaternions are expressed in hyperplanes. It's a four-dimensional quantity. And the advantage of quaternion is Quaternion do not suffer from this 90-degree pitch singularity. All the computer graphics that you are working on, all the animations that you are looking at, as a matter of fact, the advanced flight control systems, all of them use quaternions. And we will talk about, yeah.
Why do we need to look into quaternions? Because an aircraft never reaches 90 degrees.
F-16 missile.
Go
Yeah,
ahead.
so basically, yeah, and so I will show you the formulation using the Euler angle. I will show you the formulation using quaternion. The problem with Euler angle is actually quaternion multiplication. The math, it may seem complex, but when we try to use it in a recursive application like a computer algebra, or if we try to implement that on an embedded system, propagating quaternions, it's easier because it's less matrix calculation than propagating a direction cosine matrix or Euler angles. And I will show you. Quaternions do not have mathematical singularity. The only problem with quaternions is you can't just look at the quaternion and then understand what it means. So for visualization, you take a quaternion, you convert that quaternion into an Euler angle, and then you can visualize. Euler angles, you can easily visualize. Yeah, then you have pitch and you have roll. But if I give you a quaternion, you won't be able to understand exactly what that quaternion means. So to visualize, you have to take the quaternion, convert that quaternion into an Euler angle, and then use that Euler angle to understand that is the roll, that is the pitch, and that is the yaw. So we will talk about it. Now there are multiple frames. The first and foremost frame that we are talking about is, first frame is the vehicle frame. Now this vehicle frame is nothing but a pure translation about north, east, and down, so that the earth fixed frame gets attached to the center of gravity of the aircraft. Please understand, there is no relative orientation between the inertial frame and the vehicle frame. Everyone understood this? So it's purely translation about north, east, and down axis. Now, what we want to do is we want to incorporate the respective rotations. So the first rotation that we are looking at is the rotation about yaw. And that rotation, if you remember from robotics 1, is given as sine theta minus cosine theta minus sine theta cosine theta, and you have 1. But since we have flipped the frame sort of numbering, so we actually we are going from V1 frame to V frame. That's why we have to use the transpose, and that is the rotation matrix that we get. So vehicle 1 frame is the rotation matrix corresponding to yaw rotation of the aircraft. Then we have vehicle 2 frame, which is the pitch orientation of the aircraft. So again, if you remember robotics 1, this is the rotation transformation about the about the y axis. So first axis is x, y, and z. So as you can see, we have 1 in the second row indicating that rotation is about y. And that is the rotation matrix regarding y. Then what we have is we have the third rotation, which is the rotation about z. Rotation about x, which is roll. So as you can see, first row has 1 that indicates the rotation about x. This is exactly same formulation for the spherical wrist when you have 3 revolute joints that are perpendicular to each other. So you can think about it that we have the first revolute joint indicating rotation about yaw. We have the second revolute joint indicating rotation about pitch, and we have the third revolute joint that is indicating rotation about roll. So when you combine these three angles together, what you get is you get this final direction cosine matrix that gives you the relationship between the initial frame, vehicle frame, all the way to the body frame. And I will derive this rotation matrix towards the end. So you have the first rotation matrix, second rotation matrix, third rotation matrix. Once you multiply these rotation matrix, you get this combined rotation matrix. And as I showed in the last class, that small rotations are commutative because of the small angle approximation. But in general, large rotations are non-commutative, which means if you change the sequence of the rotation, the answers will not be the same. However, here is what happens. These rotation matrices are calculated at millisecond. In millisecond, theta variation is extremely small. A teeny tiny variation in theta gives you sine theta is equal to theta and cosine theta is equal to 1 type of approximation. So when you are computing these rotation matrices, or in other words, it's called propagating the rotation matrix throughout the solution at every millisecond, you can use the approximation, and for that computation only, these rotation matrices follow the commutation. So basically, they can be commutative. Now, next thing which I want to talk about is, let's look at the most important force which is acting on the aircraft. Aircraft is flying through the air. Aircraft is not going on ground. Aircraft is not on ground. Aircraft is traveling in the air. So there is a concept which is called as airspeed. That is the most important speed that aircraft instrumentation need to measure. What is airspeed? Airspeed is speed of the aircraft relative to the surrounding air. Airspeed is speed of the aircraft relative to surrounding air. Now, please try to understand that airspeed is not aligned. It's very important. Airspeed is not aligned with any of the vehicle frames. Airspeed, that airspeed vector is not aligned with vehicle frame or vehicle 1 frame, vehicle 2 frame, or body frame. That aircraft airspeed is at some arbitrary angle with respect to the body frame. Now, you can think about, and this is extremely important that I want you to understand, that if you look at the aircraft, first, this is the body frame. This is the body frame. And what I'm showing you here is this is the body frame. This aircraft, the VA, which is the airspeed, is making an angle with respect to the body frame, and it is also making an angle with respect to the projection of the body frame. So what I mean by that is, let me show you what I mean by that. This airspeed, it's somewhere over here. So what I want to show you is, imagine if you have something like this. So you have north, this is north, east, and down. We have north, east, and down. And this aircraft speed, this is somewhere here. This is VA. And this is actually making two angles. So, and it is, since it's a three-dimensional figure, it might be slightly difficult to visualize, but I want you to visualize that if this is north, if this is east, and if this is down, this VA is somewhere here. So if you think about it, it is around the diagonal, which means that VA airspeed is making two angles. And what are those two angles? So if I project this airspeed, and this is very important, if I project this airspeed onto this frame, so I want to show you this frame. If I project this onto this frame, I have this component of airspeed. So this component of airspeed is on the plane, which is this plane. And the angle made by the aircraft with respect to the projection of airspeed onto IB-KB plane is called as angle of attack. Now, I want to explain this concept again. What is angle of attack? Aircraft generates lift because of angle of attack. You have an airfoil, and what you have is you have some air velocity air that actually gets in contact with the airfoil. And what happens is, because of the shape of the airfoil, the velocity at the bottom velocity at the bottom is less than the velocity on top. So velocity at the bottom is less than velocity on the top. Total energy is going to remain constant. Since velocity at the top is greater, the pressure drops down. Velocity at the bottom is slower or less, so the pressure increases. So you get a differential pressure, and that causes this aircraft to lift. This aircraft lift is dependent on the angle of attack, which means if you have a flat airfoil, it will not generate tremendous lift. If you start changing the angle, then gradually you will get some lift and you will get some drag. At a critical angle of attack, there is no lift, only drag. If the airspeed is very low, then the airfoil will not generate any lift and the aircraft will stall. So for aircraft to fly, they need to have certain airspeed. Otherwise, the aircraft will stall and fall down as a rock. So airspeed is generated by the relative speed, because aircraft is going forward, air is coming backward. So because of that, you have a relative speed between the surrounding air and the aircraft that is generating the airspeed. So how is, okay, so there is something called as the prop based plane and the jet based plane. So propeller planes, they have those big props. So what happens, what is the function of the prop? There is a difference between the propeller and a fan. Even though, if you, at the end of the day, what you see is you have a motor. It could be an electric motor, it could be an internal combustion engine, it could be a jet engine, whatever it is. It's a motor connected to the shaft and connected to some type of a fan or some type of a blade. There is a difference between the prop and the fan. The purpose of a prop is to generate thrust. Purpose of the fan is to blow air. And what achieves this? The blade and the angle of blade actually dictates whether that turbo machinery, which is basically fan and then shaft and blade and everything, is going to generate flow or force. So for props are designed to generate thrust, and fan, they are designed to generate airflow. At the end of the day, finally, what we are doing is we are manipulating energy, whether it's a pressure energy or whether it's a flow energy. At the end of the day, we are manipulating energy. But the design of blades, the angle of the blades, the curvature of the blades, they dictate whether that electrical energy or chemical energy or mechanical energy is used to increase the flow energy or the pressure energy. So prop and fan, that is the fundamental. You can't just take a fan blade, attach it to the aircraft and expect that aircraft will fly. Aircraft will not fly. Okay, so coming back to our discussion, that airspeed vector is something like at a diagonal. So if you think about it, it is at a cross diagonal. So if you look at the projection of that air velocity or VA onto the north and downstream, what you get is you get an angle that is called as angle of attack. Yeah.
Shouldn't the VA be in negative kx?
Yeah, I'll explain that to you in just a second. Now the issue is the angle of attack, because of the sign convention, is always taken in the left-hand coordinate system. That's why if you look at the rotation matrix corresponding to the angle of attack, basically you substitute minus alpha. So, and what the rotation matrix that you get is cosine alpha minus sine alpha, and cosine alpha. So please try to understand, because of the sign convention, angle of attack is always assumed in the left-hand coordinate frame, and that's why, as you can see, that sign is negative, and that's why it is saying it is over here. That's why what you get, that rotation matrix, as you can see, cosine alpha, and ideally it should be cosine alpha, sine alpha, cosine alpha. But since alpha is taken into negative terms, so which is minus alpha, cosine of minus alpha becomes cosine alpha, and sine of minus alpha becomes minus sine alpha. So that's why you have this negative sign. So please understand, this is the convention in the aircraft nomenclature, that angle of attack is considered in the left-hand coordinate frame. That's why you have this negative sign. Now, this is not the end of the story, but we are close. Now, please understand, this airspeed vector is at certain angle. So it actually has two projections. One is projection in this plane, and second is projection in the vertical plane. So projection, if you see from here, you get alpha, and when you see from top, you get beta. And that is called as the side slip angle. So I will explain it to you in just a second. So we got into the stability frame, and the last frame that we look into is called as the wind frame. What's happening in wind frame? I want you to think about the same problem again. This is the airspeed. This is the airspeed. This airspeed, if you look at from the side, if you look from side, you see the projection of the airspeed over here. If you see projection of airspeed over here, this angle is alpha. If you see from top, you see projection of the airspeed in here, and that angle is called beta. Everyone understood this? This is, I will explain this once again. with a slightly, hopefully, bigger picture. So we are looking at a three-dimensional system. So this is sort of the three-dimensional box that we are looking at. And now what we have is and I'm going to exaggerate, airspeed vector somewhere over here. This is my VA. Now I'm going to look from side. So I look from here and I notice the projection of VA here. I see projection of VA here. This guy is angle of attack. Now what I'm going to do is I'm going to look at projection of VA in top. So for that, what I need to do is I need to go up here and maybe draw this line. And this I'm looking from top. So I see here that is beta. Everyone understood this? So these are the two angles, but that is very important. I want you to note, if this is going to be my north, if this is going to be my east, and if this is going to be my down, airspeed rotation, the rotation about the airspeed, and actually I want you to understand this for a second. So as you can see, this is alpha. Curl your fingers in the direction of alpha. Can you see it is pointing towards the negative E axis? Curl your fingers in the direction of alpha. Right hand thumb rule. That is pointing towards the negative E axis. That's why that rotation is considered negative in convention. Now, what I want you to do is, on the other hand, I want you to look at from the top, and please note you have this rotation from the top. Curl your fingers in the direction of rotation and you see that the thumb is pointing toward the down axis, which means the alpha rotation is about Y, but it is negative, and the beta rotation, which is we are finally going to the wind frame, is about the down axis in the positive direction. That's why you see that the rotation matrix that we have is of the form cosine theta minus sine cosine beta minus sine beta sine beta cosine beta. But since the sequence of the frame is changed, it's from wind to stability, we have the transpose of the rotation matrix. Everyone understood this? Once again, the convention here is wind frame to stability frame. So finally what you had is you had the inertial frame. That inertial frame we converted to, say, a body frame. So now we are at the vehicle body. We took care of roll, pitch, and yaw. After that, what we have is we have body or stability frame. So we took care of the angle of attack, alpha. This captures alpha. And the last frame that we have is stability frame, rotation, and to wind frame. And that gives me the value of the side slip angle, which is beta. Everyone understood this? Yes.
So pretty much our first few frames, that is the translation of the plane from ground to
Vehicle frame.
big frame. Yes. So wind frame and the stability frame, those are just being applied to the body frame.
After body frame, what we have is we have the stability frame, and then we have the wind frame, because at the end of the day, the aerodynamic forces are generated by the airspeed. And that airspeed is not aligned with body. So what we need to do is somehow finally we need to align that vector, airspeed vector with the body frame so that we can write down the differential equations of motion. Forces is equal to mass times acceleration. That's why this is how it is. And it may look complicated, but it's really not. So let's quickly recap. Inertial frame to vehicle frame to vehicle one frame to vehicle two frame, vehicle two frame to body frame. From body frame, we go to stability frame, and from stability frame, we go to the wind frame. Everyone understood this? These are the sequence of the frames. Any flying object will have these frames. If you are throwing a rock, it will have the same frame. If you have an airplane, same frame. If you have a missile, same frames. So any moving object. So this is the crux of aerial robotics. If you have a robot that is flying, these are the frames that dynamics will be expressed in. Now, finally, what I can do is I can combine these two rotations. And as you can see, when I combine these two rotations, I can actually have this matrix. So basically, last two rotations can be combined and cosine beta and sine beta can be represented. Again, for my own satisfaction, I need to say this. If you read the textbook, what they are doing is their convention is wind respect to stability. Can you see this? This is the wind frame. So they are going from the wind frame to stability frame. Everyone understood this? It is going from wind frame to stability frame. But the way we studied in robotics 1, 0R1, 1R2, 2R3. So the way we are going is inertial frame to body frame to stability frame to wind frame. Everyone understood this? What it means is PRS, that matrix, or SRW, that matrix, will be transpose of the matrix that is shown over here. Everyone understood this? Because their initial and final frames are reversed. It's an orthonormal matrix, inverse is equal to transpose. Everyone understood this? That is the only difference that you will have to keep in mind if you read to the textbook. So that's why their signs are flipped. Any question before I go any further? Yeah.
So with the stability frame, it's both negative, it's both rotating negative.
No. So I actually, this is something that, okay. At the end of the day, all our rotations are about north, east, and down. Do you agree with me? All those rotations are about north, east, and down. Now, what I want you to do is, I want you to look at the angle made by the airspeed with respect to the coordinate frames that we have. This angle is not in a plane, it is at a diagonal. So if you look at from here, you will have a projection on this plane. If you look from top, it will have projection on this plane. Do you agree with me? So if you were to look at the angle, curve your fingers in the direction of angle, thumb is pointing towards your negative east. That's why you have negative alpha. That is the reason why the sign convention that they use is slightly different. So that's why you have the alpha value is considered negative. This is something that I'll try to discuss it again when I actually work out a simulation. Yes.
But does that mean that it's been transposed? It's still being transposed though. twice or is it just?
No, you just want transpose once. Everywhere you substitute the value of alpha. So what? So think about it. This is the new vector. This is the old vector. There are two ways to match this transformation. You can transfer the old vector onto the new vector, or you can transfer the new vector onto the old vector. And please note that even though they are actually, you are doing the same operation, combining these two vectors, but your rotations are opposite. So that's what this is. But I will actually show you now, again, in terms of actual aircraft dynamics, what does it mean? And I want you to understand that this is a very common thought experiment. You are driving a car, you put your hand something like this. Now you rotate your hand like this. Do you feel more lift or do you feel drag? You feel drag, right? It's going down. So when you rotate like this, this is the positive angle of attack. So when you have a positive angle of attack, you measure lift. But this positive rotation that is causing lift in our sign convention because of the frame orientations is actually negative, to make sure that this rotation is causing lift, we have to have minus alpha. So I will show this concept again in simulation. But at the end, what needs to happen is we need to take all these frames and finally multiply them together and transfer the appropriate forces and velocities in a consistent coordinate frame. So this is what we talked about. So if you are in the body frame and if you want to transfer at the end into the wind frame, then what you have is, please understand, you will have to multiply frame, first transformation to the stability frame to wind frame. And this is the final transformation. So basically, one thing I want you to understand is typically forces or moments are most naturally defined in the wind frame. Why are they defined in wind frame? Because the aerodynamic force is caused by the airspeed, and airspeed is expressed in the wind frame. That's why the aerodynamic forces and aerodynamic moments are most naturally defined in wind frame. And then what you can do is you can transfer those rotations into the frame that you are defining the Newton's laws and applying Newton's laws. Now, one last key point is the relationship between the airspeed, wind speed, and ground speed. So I want you to remember this equation. This is a very fundamental equation. Ground speed is equal to airspeed plus wind speed, which means you have an aircraft that is flying in the air. For some reason, you grab that aircraft and place it on the ground. Remember, our ground is a flat earth. The speed at which it will travel on the ground is ground speed. However, when the aircraft is flying, aircraft could have a headwind or it could have a tailwind. I don't know if you fly through a commercial aircraft, sometimes the pilot says, hey, we are going to catch some headwind or we are going to catch some tailwind, and that will increase or decrease our flight time by a certain amount. So what happens is, this is the wind triangle. Basically, you have an airspeed, you have the ground speed, airspeed plus wind speed gives you the ground speed. So please understand, ground speed means if you take that aircraft and place it on the ground, that is the speed at which the vehicle or the aircraft is going to travel on the ground. Now, some important definitions, and this requires a little bit discussion. So what we have here is we have the aircraft ground speed that is defined in terms of body frame. So this is the aircraft ground speed expressed in the body frame. So these are the three terms. So U, V, and W, those are the aircraft velocities expressed in the body frame. Then what we have is, we have this quantity, which is the wind velocity that is expressed again in body frame. This is the wind velocity that is expressed in body frame. Now, it is important to know that I can find out, so velocity in the body frame, I can transfer that velocity onto inertial frame using this rotation transformation. And I want you to understand, this is body R and this is vehicle frame. Remember, vehicle frame is aligned with inertial frame. The only difference is you have velocities, translational velocities in north, east, and down direction. So I can transfer this velocities UW, VW, and WW in terms of north, east, down velocities, wind velocities, using this rotation transformation, because this rotation transformation comprises of roll, pitch, and yaw. Now, what I want to do is, I want to define the airspeed in the wind frame. So this is airspeed. This is airspeed in wind frame. And I just want to take you here. I want you to understand this airspeed in wind frame. Can you see that it is aligned with IW? Can you see that? So this VA does not have any component in JW or KW. You agree with me? Which means it does not have any Y or Z component in the wind frame, because wind frame I, unit vector I in wind frame is aligned with the air velocity. Do you agree with me? So I want you to observe here that the airspeed in wind frame, so this is airspeed, this is the wind frame, is VA 0 and 0. Do you agree with me? Because it's completely aligned in the unit vector in I direction. And then what you do is, if you want to convert this airspeed in body frame, you have this guy. This is nothing but, and this I just need to be super duper careful, and I want you to understand this. You have these components are the wind speeds in the body frame, and U, V, and W, these are the aircraft speeds in the body frame. So you find out the relative velocities is U minus VW, V minus VW, and W minus WW. I will repeat this once again. So at this point, what I want you to understand is, please note this guy, Do you see that this is in body frame? Are you with me so far? Can you see that this guy is in body frame? Do you agree with me? Dollars to dollars, pesos to pesos. Since both of them are in the same frame, I can add or subtract. Do you agree with me? So that's what is happened here. The relative velocity is the difference between U, UW, V, VW, and W, WW. Everyone understood this? Okay. And then what happens is, this is the final equation. If you look at UR, VR, WR is related to nothing but the component of airspeed, VA, in the wind frame. When you transform it back to the body frame, that's what you get with. So this is the final equation that is used for the transformation of the velocities. What that means is, again, I need to clarify this. UR, VR, and WR is aircraft velocity with respect to surrounding air expressed in the body frame. Aircraft velocity with respect to surrounding air expressed in the body frame is nothing but the airspeed. If we take the component of airspeed in the body frame, that is what is the speed of the aircraft relative to the surrounding air. Everyone understood this? And once you substitute this guy and we derive this, we get this final equation. And as you can see, the airspeed, these are the components of airspeed. This is first component, second component, third component. So once you take the square root, you get the airspeed. If you want to find out the angle of attack, you take the ratios of WR divided by UR. If you want to find out the side slip angle, you have VR divided by the total sum. Everyone understood this? This is absolutely, actually, this may look convoluted, but let me explain this once again. The fundamental equation is the ground speed is equal to the air speed plus wind speed. So Vg is equal to Va plus Vw. Now, Vg is expressed in the body frame. Then Vw is expressed in the body frame. So what I'm going to do is, if you look at this right-hand side quantity, I want you to look at this right-hand side quantity. I substituted this guy in here. I substituted this guy in here. And then I substituted the equation for this guy, which is given as this. Everyone understood this? And then what I did, I just collected the terms and I got that expression. Everyone understood this? It will take some time. At the end of the day, it's just trigonometry going back and forth. So for my own satisfaction, the fundamental equation is this. Now, this guy is nothing but U, V, W. This guy is basically body R, wind frame, VA 0, 0. And this guy is U, W, V, W, and WW. This guy comes from the multiplication of the rotation matrices corresponding to the stability frame alpha and the side slip beta. So this is the vector equation. Everyone understood this? That's all you need. And then once you have these angles defined, you can find out airspeed, you can find out the side slip angle, beta, you can find out the value of alpha, and when you don't have a side slip, you will notice that the beta value is 0 and you just have the relationship for angle of attack. The last concept in this chapter, which I want to talk about, is something called as the coarse angle. This is called as chi, and this is called as gamma. So basically, you have an aircraft. That aircraft is flying. If you look at the ground speed of the aircraft, VG, if you look at the component of the, and if you take the projection of the ground speed onto the flat earth, if you take the projection of the ground speed on flat earth, the first angle that is made by that aircraft is called as gamma. And if you look from top, the angle that is made by the VG is called as chi. So this is gamma and this is chi. So these are the two aircraft angles that are defined. And you can actually assign, you can look at in little bit more detail. And if you look at from the top, this is the wind triangle that we talked about. So you have, this is the inertial frame, north, east, down. As you can see, north, your X is going like this, Y is going towards left, and your Z is going in. And then you will notice, if you look from top, you have the angle beta. Please note, this figure does not show you alpha because alpha is not visible when you're looking from top. The only angle that you have visible is beta. You also have the heading. It means yaw, in what direction the aircraft is blowing. But please try to understand, there is always a difference between the desired angle of the aircraft and the angle at which the aircraft is going. So there is always a difference between the angle the pilot wants aircraft to go and the aircraft is going. And sometimes that's what is denoted by XC, which is again something called as the crab angle. So the vehicle has to crab in. So you have something called as the coarse angle, you have the heading angle, you have the side slip angle, and you have the crab angle. These are sort of the main aircraft angles. And again, if you look from front and when the aircraft is taking off, as you can see, you have the pitch angle, that is the angle that we want aircraft to pitch in. You have something called as the angle of attack, alpha. You have the flight path angle, and then they also sometimes define gamma A, which is the air mass relative to the flight angle. So these are the angles that are very important. And when wind speed and side slip are 0, VW is 0, beta is 0, airspeed is equal to ground speed, and then this analysis becomes super complex. I mean, super easy. So in this chapter, what I need you to understand is what are the different frames, how those frames are defined, what do we mean by different aircraft angles, what is the relationship between the ground speed, air speed, and wind speed. I'm not going to ask you to derive these expressions, but trust me that in the next class, in the next chapter, we are going to write the equation force is equal to mass times acceleration in X, in Y, in Z. At that time, we have to take all these coordinates and then express the forces and the velocities and accelerations in a consistent coordinate frame so that we can evaluate or we can derive the differential equations of motion. Everyone understood this? So the takeaway, key takeaway from this chapter is I want you to understand the different frames. What do we mean by angle of attack? What is the meaning of side slip angle? The relationship between air velocity, ground velocity, and wind velocity. And then we will use all this information to derive the equation of motion, and then we will integrate numerically that equation of motion. Okay, any questions? The next part is the differentiation of vector. And I want to quickly talk about this project that we have. And I'm going to actually solve the spacecraft problem in today's class. I will show you how it can be solved. And then what can be done is, this is the project aircraft. The dimensions of the aircraft are given to you. Every point on the aircraft, so the aircraft has some faces and some vertices. So the coordinate of each location of vertices is given to us. So what I want you to do is, after the spacecraft is constructed, replace those coordinates defined in the spacecraft by the coordinates defined by the aircraft. Then what will happen is MATLAB would construct or draw an aircraft for you. So I don't know if you have done this. The best way to do this is the entire code is given in Appendix C. So what you can do is you can copy and paste these functions inside the MATLAB, and then what you can see is here in on page 265, they have drawn a spacecraft. So what you should do is you should replace these numbers, these coordinates, by, you can use patch or you can use plot 3. Either commands are fine, and it will basically plot. So it shows you step by step how to plot this spacecraft. And then you will notice that you get a nice rendering of the spacecraft. And then you can actually perform the animation. So what I'm going to do now is I'm going to switch to my screen, and then I will show you how this would look like. So I'm going to share my MATLAB screen. So first and foremost, let me show you how this function looks like, which is the draw spacecraft. And I will also show you the Simulink code that actually generates this. So this is the draw spacecraft function, and you just have to copy the code that is given in the textbook. So Pn is the north inertial position, Pe is the northeast position, Pd is the down position. So north, east, down, U, V, and W are the velocities. U, V, W are the velocities. Phi, theta, and psi are the roll, pitch, and yaw angles. P, Q, R are the roll rate, pitch rate, and yaw rate. And finally, what I have here is t, that is the variable for time. Then here in MATLAB, I use something called as persistent variables. And these persistent variables are sort of global variables, or the variables that remain fixed, that they don't change. And then what I do is, first I substitute when time t is equal to 0. I define this function, and this function comprises of, actually I create an handle, spacecraft handle, and this function draws spacecraft body, takes the vertices, faces, and face colors, and then take the vectors north, east, down, and theta, psi, phi. So I'm looking at x, y, z, and roll, pitch, and yaw. And then I add the title and then create the graph. And then what I want to do is, actually, I want to show the simulation. I want to actually implement some type of animation. That's why I have said that every time I get a keyboard input, redraw this spacecraft. And then what I do is, and again, this is not my code, this is exactly the code that is given in the textbook. Then what I do is, I draw the spacecraft body. The important part is, I use a rotation transformation. That rotation transformation comprises of phi, theta, and psi that rotates, because our spacecraft is in north, east, and down frame. But to plot inside the MATLAB, I need to plot it in x, y, and z frame. So I have this coordinate transformation that would take from north, east, down to x, y, and z. This is just for MATLAB plotting. If you don't use it, and I saw a student, your aircraft or spacecraft will be flipped up. That is because you are in north, east, and down. So think about it. Your down is going like this, but for MATLAB, it's going like this. So you have to have this coordinate transformation. If you think about the robotics one, this is nothing but the projection matrix, which is transforming two fixed frame that have different orientation. And then actually I do a handle, then I use the command patch, and then actually I just do the draw. And then what I have done is, I want to show you the actual animation, like how the aircraft and spacecraft rotates. So that's why I have added some more terms. Then I have translated this. Again, this comes from the book. This is nothing new here. And then please understand, this is where you are going to draw either the spacecraft or the aircraft. Absolutely important. The only thing that you need to change in this code is, you can see I'm defining the coordinates of point 1, point 2, point 3, point 4, all the way to 12 points. Those are the points that are defining the spacecraft. That is where the edges of the spacecraft are intersecting. Everyone understood this? For your aircraft, clearly you will have a lot more points, but you only change this, nothing else. And this is again given in the textbook. Everyone understood this? Okay, now what is the next part? Next part is something important. So what I have here is, I have called this MATLAB function. It's again given in the textbook. I have called this MATLAB function in the Simulink. So how do I call this MATLAB function in Simulink? For that, I need to go to library browser. And here I have to go to user-defined function. And there are a lot of user-defined functions. Now, you can actually create a C code. You can create a MATLAB function, or you can call an interpreted MATLAB function. What is the difference between the MATLAB function and interpreted MATLAB function? Some of the functions in the MATLAB, they are not directly transferable to Simulink. If that is the case, you have to use interpreted MATLAB function, which means your MATLAB code will execute inside the Simulink function block. So how does that happen? So I want you to note that this function, please see that this function is called draw spacecraft, and the argument to this function is UU. So I'm supplying UU as an input, and then this draw spacecraft is grabbing this UU vector and plotting that spacecraft. So what I do is I go back to MATLAB. I go back to MATLAB. So I'm looking for, and double click here. So I say, what is the name of the function? That is draw spacecraft. This draw spacecraft function does not have any output. That's why I'm saying output dimension is equal to 0. By default, the output dimension is 1, which means the function is taking one input and sending out one output. Since I'm not sending any output, I substitute 0. Do you agree with me? Now, this MATLAB interpreted function, again, let's go back. This MATLAB interpreted function is, if you look at the input, if you look at the input of the MATLAB interpreted function, it's this vector UU, draw spacecraft UU. This is the interpreted function. So UU vector comprises of all this. So what I'm going to do is, let me run this code. And what you can see that all these inputs are actually sort of clubbed together into a bus, and that vector is fed into the Simulink function. So I'm going to run this code, and then what will happen is this code will run, and okay, so did I delete the name? Let me see. Draw spacecraft. Okay, so bear with me for a second. Bear with me for a second. Interpreted MATLAB function. I'm gonna run this and see if this works. Okay, so clearly I think let me see here. Spacecraft. Okay, I will have to restart. I'll just open this, and I will open this. So and that part, let me see, there are some questions on the Zoom chat window. You can use patch3 or plot 3D command. Then what is the next question? Airspeed is generated by the relative speed. Okay. MATLAB is taking its sweet time. That's okay. And please try to use the latest and greatest version of MATLAB, because there are some bug fixes. Okay. First, what I need to do is I need to make sure that I have the correct folder. So I need to change the folder, because if the folder is not correct, it will not run. So the Simulink file and the MATLAB file, they have to be in the same folder. Okay. So first, easy. Really. So first, run this. Change folder. Go here. Run. And then you will see. So yeah, can you see the spacecraft? Now, this is the spacecraft. And what you can do is you can change this angle. So if you double click on this, you change this angle, and can you see that spacecraft is kind of rotating? Then you can actually change this angle, pitch. You can change this angle, yaw. The spacecraft will rotate. You can change this northeast down again, and then you will notice that this thing will travel, and so on and so forth. Everyone understood this? Okay, 7:15. Yeah. That exactly I want to talk about. Just give me a second. This is extremely important. Again, this is the solution of your assignment. Assignment number 1. So now I'm gonna get rid of this. I'm gonna get rid of this. And I'm gonna run this. So what you can do is you have this draw aircraft, and this aircraft should be drawn. So interpreted MATLAB function, draw aircraft, run, unrecognized. So, okay, run, change folder, silence please. Run. Okay, can you see that this is the aircraft? This is your assignment. This is how the solution of your assignment should look like. And what I want to do is I want to show you something that I said that I will discuss. So I have a roll angle. I'm gonna say my roll angle is 0. My roll angle is 0. My pitch angle is 0. And my yaw angle is 0. Are you with me? So I have an aircraft that is in level flight. What I'm going to do is I'm going to increase my pitch angle to say 50 degrees. Can you see the aircraft pitched up? Now, when aircraft is pitched up, and I want you to observe this very, very carefully, I change my roll angle to 30 degrees. Can you see the aircraft roll? Can you see that I change my yaw angle to 30 degrees? Can you see the aircraft yard? Pitch was 50 degrees, 30 degree roll, 30 degree pitch, 30 degree yaw. Now check what happens. It's very important. My aircraft pitched to 90 degrees. Now let me start with first roll angle is equal to 0 and yaw angle is equal to 0. Let's recap. When the aircraft was pitched 50 degrees, I gave a non-zero roll and I gave a non-zero yaw. The aircraft rolled and yawed. Do you agree with me? Now my aircraft is again 90 degree pitch and I'm going to do the exact same thing. I'm going to roll it by 30 degrees. Can you see? And I'm going to yaw it by minus 30 degrees or 30 degrees. Can you see that the result is finally it's yawing or it's rotating about the vertical plane. So there is no difference between yaw and roll. So check this out. If I change my roll angle to 50 degrees, so if I change my roll angle to 50 degrees, if I change my yaw angle to 50 degrees, can you see it is the same rotation, which means I have lost 1 degree of freedom. This is gimbal lock. And I'll stop here.
Dr. Redcar, I had a question
Yeah.
about the faces matrix for the aircraft.
Yeah,
So with the spacecraft one, it was defining the faces in terms of 4 vertex points.
yes,
But with the aircraft one, I just did 3. So I just did the faces as triangles all over the aircraft. Is that fine?
that's fine.
Okay.
Okay, all right, so any other questions? I'm gonna stop recording.